Hi, my name is Samir Desai, and in this video I'm going to teach you how to predict the product when an alcohol is protected.
Hold up a second though. This seems ridiculous. What makes an alcohol so important that it needs protection? And what does it even mean to protect an alcohol? You've learned the importance of alcohols in previous videos, but let's quickly refresh. Alcohols are arguably one of the most important functional groups in organic chemistry. The OH can be protonated or deprotonated, oxidized or reduced, and, well, the point is they can go through numerous transformations. This reactivity means alcohol is frequently used in real-life applications to synthesize other molecules. And herein lies the gift and the curse. A functional group that is so easily transformed means that it may sometimes get in the way of other reactions. That's where protecting groups come into play. In synthesis reactions, you can protect the alcohol group to prevent any unwanted reactions at any stage of the reaction, and you can selectively remove the protecting group at any stage to reveal the alcohol group. Let's use a simple alcohol, like propanol, to illustrate this reaction. The hydrogen bonded to the oxygen is acidic, so if the reaction takes place in the presence of a base, like imidazole or DMAP, then a silyl ether protecting group, which will contain a silicon bonded to 3 R groups, simply replaces the acidic hydrogen. Think of it like this. You know how on a lazy Sunday you might pull the blankets over your head, protect your eyes from the sun? A protecting group acts as a molecular cover to protect the oxygen from reactions, effectively making it inert. And to remove this molecular cover, a fluoride anion will cleave the bond between the oxygen and silicon without affecting any other part of the molecule. So we're left with exactly what we started with, a propanol. There are a few variations of protecting groups, and of the following silyl ethers, trimethylsilyl is one of the most commonly used. Continuing with our previous example where we used propanol, TMS would simply replace the acidic hydrogen, so the result is this, with TMS in the place of hydrogen. Alternatively, triethylsilyl as a protecting group creates the following molecule, and tert-butyl dimethylsilyl and tert-butyl diphenylsilyl result in these molecules, following the same trend as the other protecting groups. Let's see how this information can be applied to a question. A student is carrying out a multi-step organic synthesis reaction, starting with 3-ethyl-4-hydroxypentanal, so a 5-carbon aldehyde with an ethyl on carbon 3 and an alcohol group on carbon 4, and treated with sodium dichromate, triethylsilyl with imidazole, and hydrogen fluoride. In order to determine the final product, let's take little steps and determine the product formed after each of the 3 treatments. The first stage of the synthesis reaction utilizes sodium dichromate. This is a strong oxidizing agent, and if you recall from previous videos, the site of oxidation can occur at carbon-oxygen or carbon-hydrogen bonds. There are 2 carbons that meet this criteria, carbon 1 and carbon 4. A strong oxidizing agent will oxidize the molecule of both these carbons, resulting in 3-ethyl-4-oxopentanoic acid. The next step is 3-ethyl-4-oxopentanoic acid reacting with a silyl ether and a base. This protecting group will typically replace the acidic hydrogen in alcohols, but is very selective and wouldn't react with the OH in carboxylic acid. Therefore, treatment with TMS and imidazole would not change the reactant. So let's move on to the third step and predict the product formed with the treatment of hydrogen fluoride. A fluoride anion works as a pair with a protecting group. The protecting group will replace the acidic hydrogen, and the fluoride anion will cleave the protecting group off. Since there is no protecting group, then there is no reactivity with the treatment of hydrogen fluoride because there is no oxygen-silicon bond to cleave. Therefore, we're left with the exact same molecule that was produced after step 1, 3-ethyl-4-oxopentanoic acid. But what happens if we switch the order of the steps? Will the final product change? Let's take a look at B. This time, we're still starting with 3-ethyl-4-hydroxypentanal, but the multi-step synthesis now begins with the treatment of TMS and imidazole. This time, there's an alcohol group on carbon 4, so TMS will replace the hydrogen, resulting in the following product. Step 2 is now the treatment with an oxidizing agent. Carbon 1 looks like it could be the site of oxidation because of the carbon-hydrogen bond. The oxidizing agent was able to oxidize carbon 4 and A, so will it be able to oxidize it this time? No, this is the whole purpose of a protecting group. It allows for selective reactivity, and in this case, it prevented the oxidizing agent from oxidizing carbon 4. Therefore, we're left with the following product. The final step is the treatment with hydrogen fluoride, which cleaves the oxygen-silicon bond and adds a hydrogen back in. Therefore, we're left with 3-ethyl 4-hydroxypentanoic acid as the final product. Now, the alcohol is no longer protected and has the ability to be oxidized. There you have it, folks. Predicting the product when an alcohol is predicted requires that you recollect a lot of redox knowledge and tie it all together. But you should now feel comfortable with this. Make sure to review previous videos and do the practice problems to ensure complete mastery over this concept.